In this video, we're going to look at differentiation. Okay, but in particular, we're going to look at a new type of differentiation called implicit differentiation. But before we get to that, I want to look at the type of differentiation you already know how to do so that we can make some comparisons, right? So imagine if I gave you y equals x plus x cubed. Well, you know how to differentiate that. We get dy dx equals 1 plus 3x squared, okay? But to kind of go into a bit more detail of what you've been doing, I'm going to put an extra line in here. And basically what we did to get from here to here was we differentiated both sides with respect to x. Now that's probably a different way of thinking about it. You probably think of it, oh, I need to find a derivative, so dy dx equals, and then I differentiate the right hand side. But a more correct way to think about it, or maybe a more useful way to think about it, especially for what we're going to do in a second, is to say, well, we're actually going to differentiate the left hand side and we're going to differentiate the right hand side both with respect to x. Okay, so this is kind of like a step that we're skipping over when we go straight to dy dx equals this thing. So we wanted to differentiate the left hand side, which was y, and then we wanted to differentiate the left hand side, which was this. So when we differentiate y, basically this dy dx is just the symbol we use to represent this. So differentiating y, well, the result is given by this symbol dy dx. Whereas when we're differentiating explicitly things that have x's in them with respect to x, well, we have rules to differentiate those, and we followed the rules and got the answer. Okay, so this form of differentiation is called explicit differentiation, and it's called explicit differentiation because here we've got y explicitly given in terms of x. So another way to think about it is we have the dependent variable given explicitly in terms of the independent variable x. Okay, so that's why it's called explicit differentiation, and that's the first one type of differentiation. Another way of thinking about differentiation is what is called implicit differentiation, and you can probably guess what it's going to be. Explicit differentiation was when you had an explicit formula for y. We're going to use implicit differentiation when we don't have an explicit formula for y. So in the case of a circle, for example, okay, a circle centered 0, 0 with radius r. So we could solve this for y, and when you solve it, you would have to take a square root, so we'd get plus or minus, so we'd actually get two different formulas, one for the top half of the circle and one for the bottom half. But if we solved this for y, we could then differentiate it and we'd have the derivative. Okay, but often you can't solve an implicit relationship between x and y for y, so you wouldn't be able to use that method. And also often doing it the way I'm about to show you is just nicer than solving for y and differentiating it that way. Okay, so we'd like to find dy dx for this circle. Of course, we can't jump straight to dy dx, or maybe some of you would be able to do that after practicing this a bit, but you can't jump straight to it, so we're going to use this intermediate step, and we're going to differentiate both sides with respect to x. So x squared plus y squared equals d dx of r squared. Okay, now we'll start with the right hand side because r is just a constant, so differentiating a constant gives 0. Now back over here, differentiating x squared, well, that's obviously 2x, but what happens when we differentiate y squared? This is kind of the new part of this. When we want to differentiate y squared, what's going to go here? What I'll do is I'll give a quick example of differentiating something else, which will give us a clue of what to do. Imagine if I wanted to differentiate 1 plus x cubed all squared. Okay, well, let's look at what this is. This is a function of x all squared. That's exactly what this is. Y is a function of x, right? We're going to end up, we could find a formula for y. Y is a function of x, so this thing, y squared, differentiating this is exactly the same as differentiating this. And what do? Well, we treat this as if it was just something squared. So to differentiate something squared, you bring the 2 down, you get the something back, you minus 1 from the power, and then you get the derivative of the inside, which is, in this case, 3x squared. Differentiating 1 plus x cubed is 3x squared. Okay, so we're going to follow that same thing up here. Something squared, you differentiate it by bringing down the 2, writing the something, putting a 1, and then timesing it by the derivative of the inside. So we've got something squared, we're going to bring down the 2, put the something there, put it to the power of 1, and times it by the derivative of the inside. Okay, so you should be able to follow what I've done there. I've just treated this as if it was some sort of function of x and followed the rule, which says I know how to differentiate a square. It becomes 2 times the variable down here, so 2 times the variable down here, but times the derivative of the inside because this is a function of x, okay? And there you have it. That's how you do implicit differentiation. We can tidy it up a bit now and say dy dx equals, and I can times through by a half, and this stays 0 to get rid of those, and I can minus the x over and divide by the y. Okay, and there's the formula, and notice how the formula depends on y as well. So if you had done what I said at the start of looking at this and you'd solved this for y and differentiated it, you'd get something, you'd be using explicit differentiation and you'd get something just in terms of x. What you could do is you could solve this for y and substitute that y back into here to see if you get the same formula just in terms of x. Okay, and one last thing you could do as well, just to investigate this and see if it behaves how you would expect to, is you could look at a circle. So look at the unit circle, for example, and say what happens when x is 1 and y is 0. So at this point here, what's happening? And if you look at the formula, you'd expect to get infinity because there's a vertical tangent, and you do. Or what would happen here? You can test that at the other points. Or what would happen in the first quadrant when x and y are both greater than 0? If x and y are both greater than 0, we've got dy dx is a negative number because of this minus sign out the front. And we can see when they're both greater than 0, the function is decreasing, so dy dx should be negative. Okay, so just have a look at that. Basically investigate it and see that it behaves in the way you would expect it to. Okay, I'll do another example. So imagine if we had x to the half plus y to the half is equal to a to the half. Well, this thing, and here a is just a constant. Or maybe I'll put that up here. A is just a constant. Another way of writing this is the square root of x plus the square root of y is equal to the square root of a. Okay, but we're going to try and graph this. So let's put a graph up. Okay, so why have I just put the first quadrant? Well, x and y are both under square root signs, so they both have to be greater than or equal to 0. So straight away I know that I'm in the first quadrant. A good thing to do is always to try and find the roots of curves. So when x is 0, if this disappears, well, we've got square root of y equals square root of a. Y has to equal a. So when x is 0, y is a. And likewise, when y is 0, x is a. So you can check that. I'm going to do, before I come back to this and differentiate it implicitly and see what the derivative looks like, I'm going to do one more thing, which is, maybe this is unfamiliar, but basically I'm going to say, well, the square root of y is positive, right? So if I got rid of that, does that make this number bigger or smaller? If I take away a positive number, let's pretend like we had 3 plus 4 was equal to 7. If I take away this number, I take away that, I've made the number smaller. So I know that the resultant number is always going to be less than or equal to the other side. So if I take away this number, which is greater than or equal to 0, so since square root of y is greater than or equal to 0, what's left, the square root of x, is going to be less than or equal to the square root of a, which of course means a is less than or equal to, x is less than or equal to a. And you can do a similar thing. So similarly, we end up with y is less than or equal to a. Okay, so that's just something that maybe you haven't seen before. Basically, we've found out that x can't get greater than a, so x has to be on this side of a, and obviously it's greater than 0, and also y is less than a as well. So if we kind of look at, the graph is going to be somehow bounded inside this square. Okay, but what does the graph do? Does the graph do this? Does the graph do this? Does the graph do this? Or something else, right? We're going to look at the derivative now, and maybe that'll give us some information which will help us work out what's happening. So to differentiate this quickly, we get 1 over 2 square root x. So if that was too quick, you should practice doing those. Plus, what happens now? I've got y to the half. Well, I get exactly the same thing here because remember, y is a function of x. So we follow the same procedure to differentiate it. but then times it by the derivative of the inside, so dy dx, and that's equal to 0. I can get rid of these because I times through by 2, and then finally I can solve for dy dx, and I minus this over, so I've got minus 1 over the square root of x, and I multiply by the square root of y to get rid of that. So there's the formula for dy dx. What I'm going to do is I'm going to check the endpoints. So when x equals a and y equals 0, so that's this first point, we get dy dx, so I'm just going to say y dash is equal to, if x is a and y is 0, it's equal to 0. Alright, and when x is equal to 0 and y is equal to a, I'm just going to say y dash, dy dx is equal to, now we've got a divided by 0. Dividing by 0 sends this off to infinity, or it's approaching infinity. So at those 2 points I see the gradient here was 0, and I see the gradient up here was infinite. So that means that the function is coming down from very steeply like this, and it's approaching here going to a slope of 0. One last thing I can look at is, because the square root of y and the square root of x are both greater than or equal to 0, there's a minus sign in front of this positive thing. It means that y dash has to be less than or equal to 0. So if y dash is less than or equal to 0, basically it's going to decrease down like this. It's still going to be decreasing, but it's going to approach 0 here. And that green line there is the graph of this function here, x to a half plus y to a half equals a to a half.